I'm Tosh Tambe. I'm with Amazon Web Services. With me, I have Supreet Sheshadri here, also from Amazon Web Services, and a special guest, Judd Kaiser from ANSYS, who will be sharing some of their experiences with using our AWS's graphics platform and services, and some of the learnings from that. And ANSYS has been a great strategic partner for us in this space, so it's great to have Judd here. Thank you. So today we will look at a few things, starting out first by seeing what it means to deliver graphics-intensive applications in general, and then what are the challenges with doing that on premises, and then some interesting opportunities as well as challenges doing that on the cloud, on AWS. So we look at that. We'll also look at how we actually are able to deliver these applications using some of our services that we've had for a few years now, and some new services that we launched this week. We'll also have a live demo from which Judd here will show us some ANSYS applications running on this platform. And then you'll also get to experience what it is to remote graphics-intensive applications on AWS. But to start out with, just to level set what we mean by graphics-intensive applications, here's a few examples of that. You see these applications across many different verticals. For example, in design and engineering, on the top left, you see a simulation. It's a thermal simulation for an engine block, or you've got a building design on the bottom, or in oil and gas, you do seismic simulations. Media entertainment, you've got animation and gaming, or medical imaging, and then in the middle, you've got life sciences with molecular modeling. So all these different verticals, different business processes that require applications with graphics. And the one common thing across all of these different verticals is that all of these applications are very critical to that business process, and the fidelity of the graphics that are generated and available for the user are critical within that business process. And when you typically think of where these applications run in a traditional environment, this is, I think, what you imagine, right? You see a beefy workstation like a big tower with tons of CPU power in it, and then you've got usually a GPU card in there, a couple of monitors. It's a typical professional graphics workstation. It's a beautiful picture, but when you put this into the real world, right, into the wild, things get a little more interesting, a little more challenging. And that's because typically it's not one application. It's a number of applications that are involved in a business process. Here's an example in design and engineering. You've got these different applications that do specific things in that process. For example, you do conceptual design for the exterior, the aesthetic design, but then you've got the structural engineering design. You simulate that design for physics to ensure it's a sound design. Then you do the tooling around it. All of these, there are specialists involved in this process that use these specialized applications, and they usually generate and consume data that's common across these applications. And this pattern you see across all of the verticals that you might think require graphics. And it's this typical pattern of multiple applications in a tool chain, sharing data, consuming and creating data. It's a very standard pattern. And in that pattern, when you drop a traditional workstation, this is what happens. And so you've got these really beefy workstations that are doing allowing a user to use a specific application, but then actually sharing data, working through the business process, becomes a very an arduous task. It's not easy. There's a lot of sending files and sharing files and working in silos that happens, which one makes for a really bad, broken workflow and management of that workflow, but also managing data, fidelity of data becomes a problem. So very often organizations quickly move to, at least the first stage of their evolution is moving to a central database or process management system. Again, using the design engineering vertical as an example, PLM systems are very commonly used for this. And they're great because they start allowing the business to manage the workflow and the data in a more organized fashion. But as soon as you have a more efficient system for this business process, you start generating more and more data. And when you need to pull this data back onto a local workstation to actually process it, to compute it, things start getting bogged down really quickly. So the next step that we see that happens is not just centralizing the data, but also starting to centralize more of the compute. So even on premises, you see these compute clusters that start getting built. And it's great. Data has gravity, and bringing compute closer to data makes things more efficient. That's true. However, on an on-premises setup, as soon as you start doing this, you start hitting the next roadblock, which is how much capacity do you really build? And that's a very interesting juncture in your business process evolution, because that decision, you are looking at some interesting trade-offs. Usually you have to make a choice. You have two choices, essentially, you have to choose between. One is you build enough capacity in all the right places that is able to address all of your demand through the business process. And knowing how business processes work, the demand is usually volatile. So what happens is you have an extremely underutilized infrastructure, right? So that's one choice. You have a lot of locked-in capital that's extremely underutilized. Or the other choice is you build an infrastructure for a certain level of utilization, right? An optimal utilization level. What really that means is you're making a conscious choice to not have enough capacity when your business needs it the most. When you have your peaks of demand, you essentially are saying we don't have the room to address them. The envelope is too small. So you're either then cutting corners, building suboptimal products and services, or you're waiting for infrastructure to become available and pushing out your time to market. Again, they're all suboptimal choices. And businesses are quickly realizing that those are real constraints with on-premises deployments, and hence are quickly moving their data and compute to the cloud. So this is the first big step to the cloud. And we are seeing this happening across the board, across verticals, across different regions that we are in. So now, with your data and your compute in the cloud, your envelope suddenly opens up, your capacity envelope. And you have this scalability. You can scale up, scale down, on-demand capacity. You can manage your cost and your performance and your business value, all of the goodness that comes with cloud deployments, with deployments in AWS. And you also are now able to start utilizing the flexibility of the system, which means you can actually use that kind of infrastructure that makes sense for a particular workload. So you can switch between using different instance types, et cetera. So just the flexibility of your business goes up. But even with this first huge step towards a more efficient business, you still have a problem, which is if you're still running your applications on your client-side devices, you're still moving data back and forth between your local machine and your cloud infrastructure. So you're bogging down your network, the bandwidth. There's real cost to this in terms of time and in terms of having data in both unsecure, locally, and also just in the movement of data around the world. So the ideal scenario, as you might have guessed in this evolution, is moving your applications to the cloud. And what this does is it really brings in the efficiencies of having your data, your compute, and your applications all in close vicinity of each other, so they can utilize the synergies of the system. Plus, with the global infrastructure footprint that we have, you can now deploy this across the world. So your business just has a more efficient footprint to run on. So that's why we encourage our customers to get their deployment models, because it's the most efficient way to run it. And then, as you can see with these little lightning icons, the data that you're transferring between your cloud and your client devices is also, it's much smaller and hence much quicker. It's just basically streaming pixels down, which is a much smaller data transfer problem than actually moving entire data files across. But let's take a closer look at what it really means to remote graphics. And then we can start talking about some of the challenges and some of the benefits of doing this with AWS. So this is a very high-level, 101 level graphics pipeline diagram. And what it is essentially on the left-hand side is a data model. And that's a logical digital representation of whatever business object data that you have. So in design, for example, the product design is your digital model. In In gaming, you have your character animation that is built. Whatever that data model, it's a logical digital representation. But then when you have to actually view it and work with it, there's a 2D representation of that gets created, and that's your scene, which usually is a CPU process. And then that scene is still a logical model, but to actually display it on a display device, you map it to actual pixel coordinates, right? So it's basically just what's on, what's off on a screen, and based on the screen resolution, you create a frame, and that frame is then pushed out to your graphics target device, whether it's your laptop or your monitor or your mobile device. And when you look at this pipeline, and you think about how you would remote this pipeline, you start seeing that there are two different problems you're trying to solve. The first problem is that of generating these graphics. And the parameters of that problem are different from the streaming of these graphics. Because on the front end, while you're generating these graphics, it involves a lot of heavy data that's moved across, because right until you create that frame, you're still dealing with all of the complexity of the underlying data model. So the more complex, the larger the data model, it actually is material to how you process it using the hardware. So you want to have your CPU, your GPU, and the infrastructure that's responsible for generating the graphics close to each other. Once the frame is generated on the streaming side, there's different parameters that come into play. Those are things like, what is the screen resolution? How many monitors do you want to display that on? What are the network conditions? How reliable is the network? What kind of packet loss do you have? So there's some other parameters that actually affect the quality and the experience of streaming. So there are two different problems, and hence to solve them, you have to take two different approaches and ensure that those approaches then are synergistic. And we've taken that approach. So for generating graphics on AWS, we've had our G2 instance for a while. We launched it in November 2013. It's based on NVIDIA K520 GPUs, the grid hardware. And you have two choices. You have the G2 2x large or the G2 8x large. The 2x large, you basically have 8 vCPUs, 15 gigabytes of memory, and you have basically one GPU to work with. On the 8XL side, you have 60 gigabytes of memory and 4 GPUs. So you've got these two configurations to work with. And you can also, you can do both graphics and compute. But now for compute, we have a more specialized platform, the P2 platform. But this is a general purpose GPU board. And some workloads run really well on it, extremely well. In fact, like render farms, for example, right, that use the entirety of the GPU and really don't require a whole lot of other of CPU or system memory. They run extremely well on this. If you want to access hardware encoding, for example, or do a combination of CUDA calls and OpenGL calls, it's a great platform to do this. However, since we launched this in the last a little over 2 years, 3 years now, we also got a lot of feedback from customers and partners that it's not the right platform for some workloads. And the consistent theme to that feedback was that it's too constrained, it's predefined, right? The ratio between your CPU cores, your RAM, and your GPU cores, your graphics cores, it's predetermined, both on the 2x large side and the 8x large size. And if your workload, if that balance between these three parameters, these three components, is ideal for your workloads run really well. Fantastic. But what if you need a little more of RAM than what you have available, say, on a 2x large size? The only option you have is to go to an 8x large, but then if you use only one GPU, the 8x large, you end up with 3 extra GPUs, and you're over-provisioned and overpaying for that instance. So you're either constrained or over-provisioned. You just don't have the right balance unless your workload, the signature of your workload is ideal for that ratio, for that configuration. So one of the partners that we've worked with for a couple of years now, who've used this platform extensively, was ANSYS. And they had, they provided us feedback. They also worked on some interesting solutions for this, and eventually ended up helping us build the right solution, which we'll talk about in a few minutes. But Jared, if you can share with us your journey on the graphics platform, that would be great.
Sure thing. So before I get into the ANSYS-specific graphics workloads, let me tell you a little bit about ANSYS, if you're not familiar. ANSYS is an engineering simulation software provider. We sell software that allows our customers to predict how their devices will behave before they even build them. So you can engineer the system in a computer to understand structural mechanics, thermal effects, fluid mechanics, electromagnetics, even embedded software. Entire systems can be simulated in the computer before you build them. Simulation's probably a lot more pervasive than you even realize. You know, virtually every heavily engineered product you use, your phone, your car, you know, the aircraft engine of the plane that brought you here, you know, I probably was, certainly could have been, or maybe should have been designed with ANSYS software or similar simulation software. ANSYS has been around for a long time, 40 years, and you know, we've seen a change in how simulation is used over time. In the not too distant past, simulation was the purview of experts. You know, analysts did simulation, they had PhDs in their chosen field, tended to be focused on the single physics, and it was done as validation late in the design cycle. But that's been steadily expanding, and today, in addition to the analysts, I would say you also have a lot more simulation being done now by designers. Earlier in the design cycle, and you know, a larger group of engineers that are involved. Now, in the not too distant future, in fact, it's a reality today. We're working on pilot projects. We really expect that every engineer will use simulation, and they may not even be aware of it. But they might be doing something like a field engineer responding to a service event in the field because there's a digital twin running on the cloud somewhere that's running predictions of impending failure based on feedback from sensors that are in a machine that's connected by the industrial Internet of Things. So simulation is growing increasingly more pervasive. So obviously we have a growth in the reach of simulation, but there's also a growth in the scale of simulation. These products are very computationally resource intensive. Heavy CPU, heavy graphics, heavy storage, and the growth in the scale. You know, customers are increasingly making use of HPC to solve larger problems and to solve them faster. It's common for our customers to run a single simulation on thousands of CPU cores for an individual run. Obviously, that generates huge data files. And as Tosh alluded to, that's driven our customers to a centralization in big on-premise data centers. You know, they have HPC compute clusters. The data storage does tend to stay local to the cluster, as Tosh says. And that's driven even more and more. The visualization starts to go into the data center as well. And so that's actually driven, you know, we've worked for years with NICE Software, you know, a partner company, to connect to remote graphics. So remote graphics isn't necessarily unique to cloud. You want to be able to remote into a graphics session in the data center as well. And we worked with NICE on-premise. Now, so those data centers that our customers have built are expensive and complex to maintain. And they're a fixed resource as well. You know, they have the same problem of being either over-provisioned or constrained in on-premise data centers. Now, as our customers considered how do they want to move their simulation workloads to cloud, what drove the conversation, you know, the reason they're asking ANSYS about, hey, how can we run on the cloud, is HPC. They want more cores. They see that infinite supply of cores. And you see on the bottom right just an example of, you know, one of our solvers showing that it scales effectively on Amazon to on the order of 2,000 cores for a single simulation. So you're talking about over 100, you know, high-end compute instances running for a single simulation. Now that they've released the C5s, that ceiling is going to get pushed up. You know, the performance is better, 20 gig networking. I think we'll probably be talking about benchmarks of 5,000 cores. Now, that means the data files are big. So this solution we've built on the cloud is a complete simulation platform. And it really follows the model that Tosh showed, where you have this chain of tools, and you need them all together, and you need storage, you need to be able to connect to the graphics. And so if we have large runs generating huge volumes of data, the actual engineering that's done, the useful information that's extracted from that data is done primarily interactively. You pull up a 3D graphics session and you do post-processing operations like you see in the bottom left, and you're dealing with complex 3D images that you need to be able to manipulate on screen with the data still in the cloud. And that's why we need a good graphics solution. We want an effective way to render the pixels in the cloud and stream those pixels to the end user. And the availability of the GPUs on AWS the G2 instance family, was one of the primary reasons we started with AWS on the solution. The problem was, as Tosh alluded to, the GPU instances were great, but 15 gig of RAM on the G2 8XL is not enough for our standard post-processing of a simulation like that one. We need more, typically a couple hundred gig of RAM. And so in partnership with NICE Software, they had a unique capability that was really important to us. And that was, we could actually run the software on one type of instance and offload the 3D rendering to a separate instance. And so we architected the solution where we're actually running the ANSYS software on, today we're using the R3 family. We'll probably switch to R4s tomorrow. We're running on an R3 with up to 244 gig of RAM. That's where the software is running. We actually offload the 3D rendering. So in our case, it's done with OpenGL calls, are fed to a separate G2 instance. And those two data streams, the 2D graphic stream and the 3D graphic stream, are combined in a proxy server and routed over the internet over port 443 to a local client that's running on your local workstation. So the good news is we were able to engineer ourselves this idea of combining the right instance with the right amount of compute and RAM with a separate instance for the graphics. Now, the bad news is it's complicated. We're doing all this architecture ourselves behind the scenes. When a user connects to a session, we're spinning up one machine, connecting to a rendering server that's independent. If necessary, if you get a whole bunch of users using the system, we spin up additional rendering servers in the background, and we have to orchestrate all of this ourselves. So it's technically complicated. So it would be difficult for someone else to come and repeat what we've done. And then the second thing is it's imperfect from the user experience point of view too. Today, because we're running on a server that doesn't have a graphics card, if you right-click on the desktop and set your screen resolution, you're going to find that you're limited to 1280 by 1024. Workable, engineers can work with it, but it does not meet the expectations of the end user sitting next to that big workstation that Tosh showed earlier with the two screens. They expect more. So we were able to make it work. AWS had all the necessary building blocks, but it was complicated and imperfect. So we're excited about where we go from here. Tosh.
Thanks, Judd. So as Judd explained, we had the basic building blocks, but there was some engineering that was required for ANSYS to actually get to a point where they could deploy their solution on AWS. So this nice software that ANSYS used, we got into some interesting conversations and ended up actually acquiring that company in March of this year. And what we've done is use some of that technology to make it much easier for our customers and partners to use a similar setup, which is more configurable and more flexible to run your graphics. And that's Elastic GPU, which Andy announced we launched in preview yesterday. And what this Elastic GPU essentially is this ability to attach GPU, a portion or the entirety of a GPU, to any EC2 instance. And what that gives you is this flexibility of choosing what compute platform you want to run your application on, and then attaching to it only as much GPU as you require for running your applications. It's very similar to attaching an EBS volume to your instance. And the architecture at the highest level, it's fairly straightforward. Essentially, you're running your applications on an instance, an EC2 instance, and you can choose whatever instance you want, the family, the size, and then when your applications run, the compute is happening locally, but all the graphics calls are essentially going to a proxy that's then redirecting them to a graphics attachment, which is in very close vicinity to the compute instance. And you can scale that graphics attachment up and down. So it's at the highest level, it's a very simple design, and we were able to put that together using sort of technology that we acquired from NICE and some technology we've built since. And that gives us that flexibility, which is the biggest advantage with Elastic GPU, that you have a range of instances, instance types and sizes, that you can now run professional graphics on, which previously you could only do on a G2 instance, 2x and 8x larges. And then the amount of graphics you can attach to this instance, you have a number of sizes. So we started out with 1 GB to 8 GB of graphics memory, and and associated, corresponding amount of GPU that you can attach. So you have flexibility in that size of GPU as well. And to add to that, the way that this has been architected, it's with a single tenancy dedicated hardware model, which is dedicated to that customer, to that user, and to that instance. So it's extremely secure. And you can access this capability as easily as you would access any other AWS service capability. So you can go to the console, and here's the EC2 launch console, your configuration console, and you start out as you always do, creating your picking your instance type, your size, the AMI, so the OS. You make those choices just as you would normally, and all you have is an extra field here. If I can point to it here, the elastic GPU field that's added in the configuration details. And all you do is basically choose a size there. So here I've chosen the X large size. Now that's all it takes, and then you launch your instance. You have your graphics of that size attached to your instance's launch. And if you want to change that size, all you have to do is stop that instance, change the amount of attachment, either have no GPU or change the size of the GPU, and relaunch that instance, and you have a different size GPU with you. You can also access it through the API, through CLI. It's just a new parameter to your EC2 run instances call, which is the elastic GPU type parameter, and you tell what size of the GPU attachment that you need. That's all it takes, and then your instance gets launched. And the ANSYS applications that Judd talked about is a quick screenshot of them running multiple sessions of that in this setup. And then once you set up this instance with a graphics, with a GPU attachment, you generate the graphics on that. How you stream it down, as I was talking about, is the second part of the problem. And you can use standard protocols. You can use a protocol of your choice. We also have the DCV protocol, which we acquired with the NICE software acquisition. You can use that, but you can also use a much more efficient way to access elastic GPU through a managed streaming service. And to share more on that is Supreet.
Tosh talked about the two building blocks that are required. One is generating the frame. The second one is actually streaming the frame. Back in 2013, we also launched what's called Amazon AppStream, and that was our first effort to deliver the streaming capabilities back to the end users. And just like we learned, we got feedback on our capabilities of GPU, we also got a lot of feedback from our customers that the SDK-based approach that we gave them was too cumbersome. It was we didn't have the flexibility of instance choice because all we had was G2. And then the cost of the G2 instance was super high, so it didn't fit all the application profile. So the customers gave us the feedback similar to the G2 model to kind of figure out a solution that would be giving them the flexibility, the choice, and the performance. So we went back to the drawing board and we built a brand new service called AppStream 2 that we are making it available today, which is a fully managed application streaming service that will allow you to deliver applications to your end users all via a browser. So our goal through the course of this journey has been, how can we make the generation of the frames effective? I think the elastic GPU is our next effort in trying to make that better. Similarly, how can we make the streaming experience better? And this is the AppStream 2 that's kind of coming in the play to make sure that app streaming experience is good. So the combination of these two is what's required to kind of provide a good visualization solution and to run your applications and data co-located and be able to visualize only and stream pixels. So I'll quickly brisk through some of the key benefits of the application streaming with the new platform. It's completely browser-based, so we are only offering HTML5-based browser support. Pay-as-you-go pricing, similar to any AWS service. You pay for what you use. Secures apps and data. This was the core problem that we were trying to solve, where how can we co-locate the apps, data, and the compute capabilities in a common place, so we can only stream pixels. The amount of data then that you flow back is very limited, and the pixels are secure. And then how can we scale this across our regions so that customers can use it whenever and wherever they want it? So when the feedback kind of resonated on these three core components, customers still wanted to move their applications to cloud, but whatever the technical solutions that we had didn't really meet their capabilities. But the big thing that they saw a trend in movement was making their users able to access these applications from any device, anywhere, and then make it available such that it's available to the users whenever they actually want it. So this, we saw a growing trend in all the three sectors, but predominantly we saw this data movement as a common problem in the ISVs and the design and engineering space, and that's the problem that we're trying to solve here. But it didn't matter which of the verticals we asked. The topmost ask from them is, how can you provide instant on access? Because people want these days to access the apps instantly wherever they want. And that was kind of our first ask. And we have taken an approach where you will see the applications being able to use by your end users just like they watch a movie. And that's kind of one of our core tenets and core philosophies is how we build AppStream 2. Similarly, we wanted all these advanced engineering applications not to be rewritten. Whatever the applications that you have, we wanted you to bring them to AWS, install them on your AMIs, and be able to use it just like how you're using it today. So that was the second tenet we kind of took it upon to make sure that we will not rewrite the applications. The third one was, as Tosh mentioned, these applications don't work independently. They need data, they need toolchains, they need licensing servers, they need a lot of other application interactions, and typically companies have set them up in a certain way and they don't want to change it. And we wanted to make sure that whatever the offering we did works with that set of constraints or requirements. And then as an example case study from ANSYS showed you that there are companies that have gone and solved these problems, but it requires a lot of do-your-own engineering. It requires a lot of infrastructure. It requires a lot of investment. And we wanted to completely simplify this process as simple as possible, similar to other AWS services. So we wanted to take away the notion of deploying software, management of the software, deploying of the infrastructure, managing that infrastructure, and just let AWS manage it for you. But in these advanced engineering workloads, what's more important is the consistent performance. Right? Users do not want to make compromise on the performance. Otherwise, they'll very quickly go back to what they were super comfortable with. And this is another tenet that we wanted to honor is whatever we do, however we stitch this whole solution together, we wanted to provide a consistent experience. The way we were able to achieve this is in the previous pictures that you saw, there is a GPU instance that will do the rendering, and there was a CPU instance that was doing the frame delivery back to the end user. There are certain solutions where you can actually slice the CPU to reduce the cost of the offering, but you make compromises on the application and the end user experience. And we wanted to avoid that and make sure that the end user experience is consistent, so we always provide a dedicated instance for the end user to use it at all times. This also secures the data belonging to the user without any leaks. So that's kind of coming back to the security tenet that we talked earlier. And to make this streaming experience flexible, and one of the feedback that we heard was, hey, I want the flexibility in my streaming instance. I want the flexibility in my graphics instance. How can I mix and match these capabilities so I can fit and pick and choose which type of instance I want for the workload that I want to run and for the experience I want to control. So we wanted you to give the choice both in the GPU capabilities and also in the streaming instance capabilities. So we went and re-architected our infrastructures and AppStream such that you actually have 4 categories of instance types that you can choose just for the streaming node. It could be just general purpose for a regular productivity workload. For an analytics workload, you could choose a compute-intensive workload, a compute category. For a large application such as the ANSYS, where it's memory-intensive, you can actually choose memory-intensive platform to run your streaming instance. And then there are certain applications which require you to use direct GPUs without offloading. And for that category, we also wanted to give you the graphics instances. But in the first three instances, categories, which is the standard compute and memory, we will provide you the ability to attach the elastic GPU that we just talked about it. So you can pick and choose your compute instance type as well as the way you want to use the GPU. So the combination of these two flexibilities will allow you to control the cost of how you want to deliver the experience to your user. You can optimize the experience based on your workload pattern. You can optimize it based on the geographical location or based on the way you want your users to collaborate. And I just wanted to summarize a few things that the AppStream 2 does in order to provide you the streaming experience. Because when you run your application, the application gets generated, the frame buffer gets generated either by the direct GPU or through the offloaded GPU. But then the streaming experience is what dictates whether this whole visualization can run on AWS or not. For that, we actually wanted to make the end user experience very simple as such as like a web app experience. So we went back to the drawing board and designed a client experience whereby it's completely HTML5. So our goal was we wanted to make sure the end user uses these applications just like they use web apps, how you interact with your multiple apps. And then when you run multiple applications on the same machine, you typically interact with them as if they are running locally, and then you want to do the same set of operations. You want to copy something from application 1 and use it in application 2. You want to share data between application 1 and application 2. You want to print something, and it could be a document that you could print, or it could be a model that you want to visualize in a full screen. So we wanted to make sure that we gave you all the capabilities that you're used to it, but all in the context of a browser, whereby the application is running on AWS. And here's an example where if I really wanted to focus on one visual model and I want to work on that model, we wanted to give you the full screen experience so you can have the immersive experience that you would have when you were running the application locally. The way we did this is through the inspiration from ANSYS. They were using nice DCP protocol. They were using it in the do-your-own engineering model where you saw a picture where there was a 2D stream coming in, a 3D stream coming in, all getting routed through a proxy. And that setup had its own set of disadvantages, and we decided, let's simplify that. And we went and re-engineered that aspect of it, whereby we actually combine those streams both at the streaming instance itself so that you get a much richer experience and you get one stream back to the end user. This whole stream is now securely encrypted from the browser all the way to the instance through a gateway, which allows the traffic to go through port 443. So all your pixels are encrypted end to end, and it's going over a secure channel. And this way, whether it's a 2D stream or a 3D stream, it follows your same set of security controls that you enforce. The other important thing we did is we wanted to make sure your data is secure, and the streaming instance was never exposed to the world. It's always fronted by a streaming gateway that prevents your instances from accessible from the public world. Because these instances have direct access to the data and your corporate resources. So you wanted to make sure that your instances are absolutely secure and follows your security controls. This is just a brief example of how you do a setup. I'm kind of setting the stage for the demo that's going to come. What you would see is, let's say I wanted to use the elastic GPU and AppStream 2 to do the same workload that we kind of saw through the ANSYS use case. If that was the use case that we were going after, I would start with an image builder. An image builder is, again, a web-based tool that we will provide to you, where you go construct an image. In this case, I would build an image with all the ANSYS applications that I want to make for my end users to be usable. I will create an image. I'll take that image and provision a fleet. In this case, I'm not provisioning those two instances that we saw, a dedicated G2 and a dedicated R3. All I'm telling AppStream 2 is I want to run a fleet. I want a memory-intensive application. This is a memory-intensive application, so I'm going to choose memory-optimized compute. I'm going to enable the check mark that Tosh showed, which is enable elastic GPU. You choose how many ever units you want it to be, and then you say provision the fleet with your scaling policy. At the end of the day, once the fleet's up and running, you have a stack which has an endpoint, and you apply your necessary policy controls, and then the stream is ready for accessible. Now you generate streaming URLs for your end users, and you actually just stream the applications from the browser. But what's happening here in this picture is you actually have a streaming gateway that's protecting all your streaming instances from getting exposed. This streaming instance now actually has access to your HPC cluster, all your database servers, and it also can be accessed depending on your routing rules, either directly from the public internet or from your on-prem network. So this is what we earlier talked about working with your IT is where if this VPC that you have set up, you don't need to change any configurations. These streaming instances are actually provisioned in your VPC. That way, it's publicly available. And all the traffic will either flow through this gateway, either through the public internet if you choose to, or through your corporate network on through this gateway. And then, just like you can attach elastic GPU through APIs, we also wanted to give you the same flexibility for managing your streaming instances so that if you're running a HPC workload, you actually want to manage your the visualization as well as the generation of the frame all through programmatically. Let's say you want to kick off a job, the job runs some visualization workload. It would interact with this streaming instance, bring up a visualization node. You would interact with the application, generate a model, kick off another job which would do the computation, and then finally you would kick off a third job which would actually do the visualization. And when you choose the visualization job, you can pick and choose, do I want just compute instances, or I want an instance with GPUs. So this gives you the flexibility to pick and choose what type of instance you want, depending on the stage of your job and the pipeline. And then finally, we didn't want to stop our APIs just for the provisioning and management. We wanted you to have the ability to generate a streaming URL, just like how you go to a web portal and access your resources. So whatever the stack you set it up, we wanted you to have the flexibility to go generate an API and say, I want to generate a streaming URL for this application stack that you can give it to your users so that they can access it from a browser. Alternatively, you can make this API call from your portal so that your users will get a seamless experience. So let's say you had a button called Launch App from your portal for the visualization workload. The user is coming and clicking on Launch App, which is making this API call. And then what you get back is a URL for which you're redirecting your users so that the whole visualization experience is happening in your portal. Oops. So I kind of talked about how elastic GPU could be used along with AppStream, how you can do without elastic GPU. I think what we wanted to do next was invite Judd back on the stage to actually do a live demo of ANSYS app running using elastic GPU and using AppStream too. So in this example, what you will see before I pass on to Judd is you will see an instance C48XL. That's the instance that's running the ANSYS application that will be accessible through the AppStream web browser. And that C48XL instance is actually offloading GPU calls to a remote GPU farm that they didn't have to set up. All they had to do was go create an image, launch a C48XL, enable GPU, and generate a streaming URL. That is what is being used to use this application. This specific instance has a really large memory footprint that is applicable for that that's suitable for that application.
So before we show you, the beauty of where we are today, I'll show you where I actually am, yesterday. The solution that we had to kind of, engineer our own elastic GPU, if you were. So how that looks like in the ANSYS Enterprise Cloud is, we have a web UI that's used for the whole simulation process. You manage your batch jobs, you manage your data, and then when you want to work interactively, you connect to an active interactive session. So this is what an interactive session in Enterprise Cloud looks like, right? So it's 3D graphics applications. You can interact with it. It's multiple windows. It's a full Windows desktop. And it works. And the upside is I'm running in this case on an R3 2XL that has 61 gig of RAM, so it's got an appropriate amount of RAM, and it's using a GPU behind the scenes. The downside is, as you can see by the kind of ugly semi-square 4:3 aspect ratio, I'm limited to 1280 by 1024. The other thing is it's actually running in a thin client. So I had to download and install a thin client that's catching the pixels as they come and displaying them for me. So I've got a thin client that's running on my application. Now, if you contrast this with what would the experience look like in AppStream 2, and it's entirely in the web browser. So this is the launch screen for AppStream 2, and it's got in a built-in application stack that they referred to. This is configured to run Workbench, ANSYS Fluent, Firefox, or an open office spreadsheet system. It's all entirely within the browser. I can switch. I've got a series of applications that are running now. So Supreet showed you the tiled view of all of the active applications you have running, and this is the same model I was just showing you in our current with the thin client running in the browser. And I can, what's nice is I can even go full screen. And it's using the full resolution of my local machine. So it really looks like the user experience that the end user expects. It's using his whole screen. It's nice high resolution. It's still using that nice DCV protocol, which is efficient in terms of the amount of bandwidth that's required. It's not super sensitive to packet loss. It's configurable. So if you go to a settings screen and so show your settings, you can trade off. Do I want maximum quality or am I concerned for best compression? And if you go to best compression, you see that the image gets a little fuzzy while you're spinning, but then when you stop, it renders nicely. And that's actually really usable the engineers often, while they're spinning, it doesn't have to be rendered perfectly. And the trade-off is I'm using much less bandwidth that way than if I go for best quality, and it stays pretty while I spin it, but now you notice I'm sending more bits across the network. And I can see I don't have, the latency is good because we're running here in US West. But the flexibility of being able to, be connected to an instance that's connected to an elastic GPU, like I said, this being a C3 8XL has all sorts of compute power for local solve. So you could really deliver, some high power usage to the end user. And if I want back to those controls, like if I want to switch between applications, the ANSYS products are kind of fundamentally multi-window, multi-application. And actually, we played with AppStream version 1 as well. We've been partnered with AWS on a number of things. And the early versions, it didn't handle that multi-window very well. So that it now handles multi-window very nicely. It's easy to switch between the main Workbench window and the mechanical window or the CFD post window. Interactivity is excellent. It really does feel like I'm running on my local workstation. In terms of utilities that help you for the overall process, as Supreet said, you can cut and paste from session to session or from your local clipboard to the cloud. You've got access to file system. This result file is a little over a gigabyte in size, so I had to upload that to play with it, and it's there in the local file system. And that shows up as a mapped drive. If I were to go file open, I browse to, I think it's the X drive or something, and it's there. Was there anything else you wanted to highlight here, Tosh? I feel like I'm missing something.
The other thing I would say is, this session URL, you could actually open that through multiple devices. So I don't have one handy here, but if I had an iPad or something and I wanted to view what Jed was doing, I could just essentially, in a browser, open the same URL and open up a collaborative session with Jed. So the simplicity of this solution is really what's beautiful. And you can, in multiple use cases where an individual user running a high-performance application remotely can run it well, but also then, because of the global footprint of AWS, can now create these collaborative environments where multi-site teams can collaborate very easily through this solution using applications which fundamentally need not be rewritten or re-architected for this experience.
Yeah, and do you want to switch back to your presentation mode now, right? So,
yep.
Okay. Good.
Thank you, Jed.
Yeah. And I'll leave it up and running, so if anybody wants to come.
Yeah, yeah. So yeah, if you guys want to play with it, you guys can. So you know it's real and not video. And so just to quickly to end this session, what I would say is if you're a software vendor, a software developer or vendor, really my ask to you is this is a powerful platform, and we really believe that your customers, our customers, would benefit from using this platform for running your application. So my ask to you is if you're a software vendor or a developer, to one, make it possible to run your applications on AWS on this platform, and that would involve making the licenses mobile, deployable on AWS. But more importantly, we would like you to certify this platform for your application. And to do that, we have set up an AWS graphic certification program through which we will extend AWS credits, co-marketing funds that will help you both certify this platform for your application and also help create awareness within your customer base on the availability of the platform for your application. So I encourage you to certify this platform, and we'll help you out with, as I said, with credits, with funds, but also with expertise, both technical and business expertise from our partner team to do that. So for your desktop or your existing workstation applications, that a quick and easy way for your customers to start using this platform for running them. And then on the other hand, you can also use this solution, especially with AppStream 2.0 and this easy way to bundle up applications and deliver them through a browser. You can use that for running your trials, your training for your employees or for your customer base, and for quickly creating SaaS environments where you can deliver your software through a browser with no engineering or no re-engineering of your software, which is a very powerful mechanism for delivering for your application for the use cases. So on both sides, I would encourage you to, one, make your applications deployable as is on this platform, and on the other side, to provide these access points for training and trials, et cetera, through the AppStream 2.0 solution. And with that, we're at the end of the session. So first of all, thank you for your time. And we have about 6.5 minutes here left. So we are open for any questions that you guys might have. Oh, thanks, Chet. Let me, so since we were talking about certification, here's how we actually get to that. So this is the EC2 page. And on that, you will see on the left-hand side the Elastic GPU menu, and it'll take you to the Elastic GPU page where you have the description of the service, etc. But also right at the top, you see the sign up for Elastic GPU preview button. And if you click that, which I have, trust me, it should go to there you go. You go to a page where you can register for the preview. Now, we are giving priority to software vendors right now for the preview because we really think that the more applications that certify this platform as early as possible, we will be able to have more customers use this platform when we go into general availability. So we are prioritizing the preview for software vendors right now. And if you're one, please go fill this out. If you're a user as well, you can go in and indicate what applications you would like to run here. And if you're a customer, you can also speak to the application vendor and make sure that they are taking advantage of the graphics certification program and certifying the platform. All right, thanks, Jed, for the reminder. Now we can go into questions if you have any. I think I had one there.